Hello everyone. We are from group
Admiral Jerry.
Admiral Jerry, and today we're gonna explain to y'all how the messenger satellite works. My name is Brian Chatraguna. My name is 136171115.
My name is Jeremiah Hasanatan. My name is 136171110.
My name is Muhammad Fadil Primaniko. My student ID is 136-17103.
And my name is Gunawan Evan Pristiwaji, student ID number 136-17119.
Okay, we hope you all enjoy this explanation about the messenger satellite. Bye.
So, a bit about the messenger satellite. A bit of a general overview that the messenger stands for Mercury Surface Environment Geochemistry and Ranging. Its mission type is for Mercury probe. It is operated by NASA. It has a COSPAR ID of 2004030A, SATCAT number 28391. It has its own website. You can search it on Google. And one of the most important data to know is the mission duration overview, which has a total of 10 years, 8 months, and 27 days. It's the messenger probe revolve around Mercury for 4 years, 1 month, and 14 days, and its en route from Earth to Mercury for about 7 years of journey. Its actual first primary mission was 1 year, then extended for the first time for another year, and then the second extension for 2 years. So that's about the general overview of the Mercury probe messenger. And now about these spacecraft properties. The messenger was manufactured by Applied Physics Laboratory of Johns Hopkins University. Launch mass of 1.107 kilograms or 2,443 pounds. Its propellant mass was 607.8 kilograms, and it has a power of 450 watts. Next, the messenger was launched from Cape Canaveral Space Launch Complex 17B at Cape Canaveral Air Force Station Space Launch 17 in Florida, USA. It was located, US is in the northern hemisphere, but Florida isn't very that north, so it has a quite, and I think it's quite efficient as it was quite near to the equator. So the location was at 28 degree 26 minute 48 second north, 80 degree 33 minute 58 second west. It's operated by a joint of NASA and US Air Force. It has until now it has a total launch of 325 before being closed. It has 2 launch pads, A and B, and has a minimal and maximal orbital inclination between 28 degree to 57 degree. So here is the map of the Cape Canaveral Air Force Station, bird's eye view from the space. So you can see that it's in the state of Florida in United States of America.
And for the mission overview, the purpose of this mission is to map the surface of Mercury and to study Mercury's chemical composition, geology, and magnetic field. And this spacecraft will travel to Venus from Earth using Hoffman transfer orbit, and in the end of the mission, this trajectory will orbit the planet Mercury. This is the Hoffman transfer orbit that we will use to travel to Mercury, and we can know the pericenter by knowing the distance of Sun minus Mercury, and the epicenter is distance of Sun minus Earth. and we can determine the semi-major axis by adding pericenter plus apocenter and divide it by 2. And we can also use Fish-Viva equation to determine the velocity at the orbit pericenter and apocenter.
So here, we determine the velocity of the spacecraft, the apocenter and the pericenter using the Fish-Viva integral. So what we need to do is just plug in the gravitational parameter, the distance from the Sun to the Earth, and the semi-major axis of the orbit to determine the velocity at the apocenter. To determine the velocity at the pericenter, we just plug in the distance from the Sun to Mercury instead of the distance from the Sun to the Earth to determine the velocity at the pericenter, which the values you can see on the slide. In this section, we will determine the amount of delta V needed for the spacecraft to establish its hyperbolic escape trajectory. First, we will need to find the initial velocity of the spacecraft, which will be the velocity of the circular orbit when it is at its parking orbit, which we have determined to be around 7.77 kilometers per second. We now need to determine the velocity of the spacecraft at the pericenter of the hyperbolic escape trajectory. First, we need to find the semi-major axis of the hyperbolic orbit, which we can find using the equation V infinite equals the square root of mu over minus a. From there, we can determine the semi-major axis, and then we just plug in the mu and a, and then the distance of the pericenter into the Fish-Viva integral to determine the velocity at the pericenter of the hyperbolic escape trajectory. Now, we can determine the delta V required to establish this escape trajectory by subtracting the velocity at its pericenter of the hyperbolic orbit with the velocity of the circular orbit. Now in this section, we will determine the velocity of the spacecraft when it is at the pericenter of the hyperbolic arrival trajectory. Using the similar steps as we did before, first we determine the semi-major axis of the orbit by using the equation V infinite equals square root of mu over minus a, and then again we use the Fish-Viva integral to determine the velocity at the pericenter of this hyperbolic orbit, which we have determined to be about 10.456 kilometers per second. After the hyperbolic arrival orbit, we want the spacecraft to go into its elliptical orbit with the pericenter of 2,639 kilometers and an apocenter of 11,739 kilometers. From there, we can determine the semi-major axis of the elliptical orbit, and then again find the velocities at its apocenter and pericenter using the Fish-Viva integral. After this, we can now determine the final delta V required to turn the hyperbolic arrival trajectory into the final elliptical orbit.
Okay, so now for the period. By period, this means that it is the time it takes for the satellite to get from the Earth until it gets to the Mercury orbit. All right. So period, or we denote it as P, is equal to h squared divided by mu. H means that it is the orbit specific angular momentum, and mu is the gravitational parameter. In this case, we're using the gravitational parameter of the Sun because the Sun is the main body that makes the satellite orbit, and makes the satellite can get from the Earth until Mercury. So, and the H itself has its own formula, which is the R. The R means that it's the instantaneous radius of the orbit at a particular position, and v is the velocity at that particular position. And what's interesting is that the h always stays the same, because as the satellite moves from the radius from a higher radius to the lower radius, the speed also the speed increases. So it's kind of, it cancels out each other in a way that it always makes the h constant. So in this case, to calculate p, we use the gravitational parameter of the sun, which is 1.327 times 10 to the 11, and we use the instantaneous radius of the satellite, using when it's in the apocenter, which is 1.496 times 10 to the 8, and it has a particular velocity of 22.3 km per second. Then we square it and we divide it by the gravitational parameter, and we get the period is 486 days. And in this case, since the orbit is only half of it, so we divide it by 2, and in this case the 486 days is already half of it. So the next one is the propellant mass. To design a mission, we essentially need to know what the propellant mass is before we launch the satellite, because we need to be able to fit all of the propellant mass inside the rocket before we launch it, so that it gets the sufficient propellant mass it needs to get to the destination. So the propellant mass has a formula of follow. Mf equals to mo, then open brackets 1 minus e to the power of negative delta v over g, and times the specific impulse, where in this case the launch mass is means that it's the mass before it is launched, and basically it's the initial mass before the propellant is used, and it is 1,107.9 kilograms. And the gravitational acceleration in Earth is 9.98 meters per second squared, and in Mercury is 3.7 meters per second squared. Okay, I think we need to correct this one, because this means that it's the G naught Earth. And the rocket basically, and the specific impulse basically is a property that the rocket has, and so it has a specific impulse of 286 seconds. Alright, so in this case, there are two delta V's that are performed in the whole mission, which is, first, we need to launch the satellite from the first parking orbit, and it requires a delta V. So therefore we need to know the propellant mass needed for this maneuver. Alright, for the first one is basically the hyperbolic trajectory. We use the launch mass of this 1,107.9 kilograms, then open brackets 1 minus e to the power of the delta v, which is 5.54 kilometers per second, then divided by the gravitational acceleration of Earth, which is 9.98 times 10 to the minus 3. This is because we need to convert it to kilometers, and times the specific impulse. And that gets us for the first propellant mass needed for that maneuver is 984.8 kilograms. And for the next maneuver is the one where we decrease the velocity when it transitions from the heliocentric orbit into the orbit that the Mercury captures, where the Mercury captures the satellite, and the delta V is 6.765 kilometers per second, and we use the G of Mercury, which is 3.7 meters per second squared, and that gets us 1,106.2 kilograms. That means that it requires more propellant mass to capture the satellite from the heliocentric orbit than it is to launch it from the Earth into the heliocentric orbit. So to get the total mass needed, the total propellant mass needed is you just add them up, and that equals to 2,091 kilograms.
Alright, so to wrap up the presentation, here's a comparison table between the mission calculation and the live mission. So for the mission calculation, so we have two data here about the V infinite, which are the hyperbolic arrival is 9.62 km per second, and hyperbolic escape is 7.484 km per second. Unfortunately, the live mission exact value is unknown, and the days of the mission calculation is 486 days, while the live mission, the actual mission, took nearly 7 years or 2,555 days. Why? Because here we don't assume that the time, there is no waiting time for the orbit to be synchronized, so you just burn and directly go to the next orbit. And about the propellant mass, here our mission calculation is valuing about 2,091 kilograms, while the live mission is just 607.9 kilograms. So why is the propellant mass is soaring higher than the live mission? It's because the time. So, to conserve time, we burn the propellant so that we don't need to wait for the orbit to be synchronized. But the downside is we need a lot of propellant. While the live mission, they're a bit more patient, waiting for the orbit to be synchronized so that they don't waste any propellant. They use it as minimum as they could, so that using cosmic billiard, they can reach Mercury with the less propellant. I guess that's all for our presentation. Hope you enjoy it. See you next time.